All right, I wore a tie just for this event. Got my family tartan here, so we're in good shape. Want to be all proper like. Um, so kind of got a couple different topics here. I wanted to kind of take a view through designing for additive with a particular perspective, maybe from a materials and process engineer's point of view. I think that this has largely been underrepresented in the conversation. You can't have a repeatable and reproducible process without consistent material feedstock. So that's kind of my thinking here. So if we think about, I borrowed these slides from Tim Simpson and Duan's DfAM symposium at Penn State, similar material, reprising for this role. So the future is a team sport. So much like the F-117 stealth fighter, advanced manufacturing and advanced systems are about system integration and system design. So this is about, and if you just take the simple example of a powder bed fusion device, there's a lot going on now in this machine. It's much more complicated than a sand casting. We're creating a material and a microstructure while we're creating the part. So there are a lot of things that are happening. You need a lot of interdisciplinary engineering happening there. So an integrated team. So pretty much everything in the future I see as being kind of team-based. So I made this analogy at the DfAM symposium, which personally I thought worked. So it was really that the idea that designing for additive is somewhat similar to being a chef. So when I initially brought up this topic, a few people in my head, I've been watching The Bear, so I'm thinking, yeah, this is me. I'm the bear. I'm telling everybody what to do. We got the, we're grilling things over here. We're sautéing things over there. Naturally, Gordon Ramsay, I thought, hey, this is a good character. He's barking orders. He's telling everybody what to do. He's shouting at people. Some of my team, maybe thought the British Baking Show was more my speed, and yet a few others, brought up the chef from the Muppets. So, maybe with that as a entree, we'll kind of keep going. So if you take designing for additive as a team event, and if design teams were like chefs design a meal. They don't design a single dish, they design an entire meal. So you start with an empty plate. You may have a meat or a protein, but you'll probably have starches, you'll have vegetables. You may have multiple courses like a salad. All of us like a nice dessert. That's always good. And then all of that needs to be paired with what kind of beverage that you're having. That is a meal. So it's not just about cooking the steak. As people like to say, you sell the sizzle, not the steak. And I specifically chose the 3D printing industry as opposed to the additive manufacturing industry. So when the 3D printing industry sells the sizzle, most of us on this call are probably more interested in the protein and the nutritional value of the steak, and what it does to sustain our army of engineers that are out there. So when we think about this perspective on the TBGA side of things, this is the opportunity space. We're creating a meal. We have all kinds of opportunity. We can have as many courses as we want. We're unconstrained. This is what we call DfAM. And the reality is that chefs live with requirements, and some cases you will have customers who are a vegetarian or can't have gluten or cannot tolerate lactose. So you also can be constrained by the method, in this analogy, the manufacturing process, if you will. You may have an oven, you may have a grill, you may have an open flame. You need to adjust your desires to what you can practically make. And so just this morning, there was a clever conversation happening between Mark Kirby and Duan on the LinkedIn about microwaving a steak might not be the way to go. Microwave is a very useful tool if you wanted to heat up water and get it to boiling very quickly. Probably not the best choice if you wanted to cook a steak. So inadvertently, you guys did a fantastic job of making a point for me. So kudos. But now, when we talk about MFAM, we're talking about sort of the restrictive side of things. You're constrained by what your customer wants. what you have as inputs, what you have as processing technologies available to you. Those start to put constraints on what you can do with the design. So these things also need to be taken into account. So again, on the TBGA side, we look at this designing for additive as MFAM plus DfAM. The designers have to balance the restrictive and opportunistic aspects for additive. Simply saying that, a lot of times we're constrained by the additive process on the MFAM side, whereas on the DfAM piece, we're thinking more about the part. We've got great ideas about what we could do with this part. We may have all kinds of opportunity there. Just a way to kind of break the problem up. So we talk a lot about requirements. Obviously there's a lot of things that go into an AM process. This one's more or less honed in on powder bed fusion. Don't need to go through all of it, but there are requirements here. There are different things that we need to take into account. We have a build layout. We have support structures, which could act as structural or maybe thermal. The design guidelines. What GD&T, what features do we need to add? The processing parameters dependent upon the material and the feedstock and what we're looking at. All the post-processing. How are we going to heat treat when we're finished? Do we need to do mechanical processing? Do we need to do chemical processing? And then, the last step is, how do we prove that we made what we said we were going to make? So this is the volumetric and dimensional type inspection processes. So again, just to kind of give a flavor that, for us, designing for additive has to leave the part ready to be bolted on, installed, ready for flight or whatever service that it's going to go into. Similarly, we've derived this the maturity model approach. So as you step up in product requirements, you have to increase the skills and knowledge to get you there. So at level 0, this is the prototyping world. So pre-production, you're kind of testing out processes, you're testing out shapes. Requirements aren't too high, so the skills and knowledge, you're learning. And then you get to level 1, we're talking about production influence. We're not making the part with additive, we're maybe making the tooling, or maybe making a shop aid that is influencing the actual part. But we're increasing our knowledge, we're increasing our MFAM ability. We have to start tracking the tooling, etc. And that leaves us at a little bit higher level than we were at. Then we get to level 2. This is the most disdainful place to be, where everybody just wants to make the same part that they've been making. Largely that's been optimized for some other manufacturing process, and most of us will have lived this existence and have scars to show from it. And sometimes you're stuck here because you need, so if it's a spare part, for example, you don't have the ability to redesign the part. You're living with the reality that it needs to look like, the part that it's there to replace. And so this is really heavily MFAM. You're in the restrictive space, but we've made a big jump from the previous level. So we need specifications, we need materials database, et cetera, et cetera. Then you go to the more entertaining place. That's a more opportunity space because you can unitize parts, eliminate joints, increase the complexity, and maybe improve performance. So now we're starting to look more at DfAM. We're really good at MFAM. We're using advanced tools like generative design, etc. And then at level 4, we're talking about parts that really can only be made by additive. And so some of these great heat exchangers that you see are really good examples here. And to get there, you have to have very high DfAM and MFAM skills. You need to have a holistic design process. Your team needs to be trained in additive. Similarly, we talk about the readiness model. So we divide this world up into 4 segments: the machine, materials, digital, and people side of things. So as you're progressing in the maturity model, you really can't get there if you're mismatched in one of these categories. Not saying that you need to be at the same level for all of them, but it's going to ease your path into it, and just something to take into account. So what we're going to talk about is Metal Powder Works, and what is Metal Powder Works. So with that menu to digest, see what I did there? Chef analogy. We want to talk about the world of powders. So Metal Powder Works has invented a new process. It's a very different way of manufacturing metal powders. It's not atomization, Modern day atomization has been around for about 90 years. It's pretty leaned out. Metal Powder Works is inherently lower cost. It's more sustainable. We have very low CO2 emissions, much different than atomizing. We can produce high quality, very consistent. It's a very high yield process, so typically 95% size yield efficiency. Can be safer because you can match the rate of production. It's a continuous process, so you can match the rate of production to the consumption, and it can do metals and polymers. So we're pursuing metals at this point in time. Clearly, we named the company when we were only looking at doing metals, and later learned that we can also process polymers. But what we're talking about is a step change in production and consumption. And so we can produce at our facility. We can also produce at the point of need. So we'll kind of run through some of these examples. So what do? We sell metal powders today, mostly aluminum and copper product. We've recently announced at Formnext, we announced this partnership with the Team Aero, the Australian race car team. So these are two components that go into the steering housing, 50% lighter than what was there previously. So we're showing that our technology through a powder bed fusion printer, thanks to the fine folks at Beehive 3D, printed this at the former Volunteer Aero facility. Printed our powder in conjunction with HRL, so we used the 7000 series aluminum powder. HRL coated it with their inoculant, Beehive printed it, and now these parts are being installed and running on the car. So, with this, we're showing that the powder, can in fact be printed. It doesn't necessarily look like atomized powder. Usually we get a lot of comments around the sphericity, etc., but we'll cover that in a second. Our second mode of operation will be through machine sales, so we're not ready to do this in 2022 or 2023, but because we're efficient and because we're a continuous and a room temperature process, our equipment could be deployed either next to a printer, feeding directly into a DED or cold spray type machine, or in a spring and dashpot situation to powder bed type printers, or with producers today that let's say they typically might consume more than 5 or produce more than 5 metric tons at an aluminum density. That this is something that could be appealing to them. The other option that we have outside of the machine sales is powder by the hour, and this is effectively equipment leasing. So the customer, so in this instance, we charge an annual rate for usage of the process or the equipment, and then if you need more powder in a given year, we simply have a $1 per hour basis from which to operate. It all goes back to the process is continuous. The process is very highly efficient. 95% is yielded. So this enables you to operate in this kind of mode. The short way of thinking about this is now customer buys bar, generates powder when it's needed. You no longer buy powder. Powder is there for minutes at a time, and we progress beyond the idea of needing to stock hundreds and thousands of kilograms of product, all of which likes to pick up moisture and humidity and maybe pyrophoric and creates other issues for you. From an accounting standpoint, it's a lot easier to be storing, let's say, $9 a kilo aluminum bar than $150 a kilo aluminum powder. So how does the process work? We use a round bar as a feedstock. We have a proprietary tool that contacts the rotating surface. Our algorithm controls the size and the shape, and it's all achieved at room temperature. Basically, if atomizing is producing a mound of powder and then you sift through it and mine out the bins that are interesting from a size, in this instance, you tell us what you want and we just make that. So with that, we'll see if this video works. So there you have it. You know, the powder, you saw the powder being collected. That happens at room temperature. It happens in real time. It's continuous. And so, you know, what you would have seen in that collection system is after it's run through a check sieve. So, you know, it is basically ready to go. The equipment, we're in the process of improving, you know, the production configuration of it. So what you see there is a slightly earlier version of it. So with our process, we can tailor the size and the shape of the powder through our numerically driven process and through the tooling geometry that we choose. Typically, we have been producing what is looked at here, this what we call equiax particles, a little bit prismatic, but we've also produced platelets and we've also produced some high aspect ratio material along the way. If you take the product and you run it through a spherodizer, you also get nice round particles. So that's also a potential output of our process. So as we all know, you know, the different processes actually desire slightly different things. You know, typically the size differs a little bit, kind of depends on what you want to get out of the final part. The ability for different processes to process different sphericity. You know, sphericity is a range. It is not a binary. You are not spherical or non-spherical. It's simply just a continuity description. And different processes can tolerate different levels of sphericity. And I did a simple category here. You know, if atomizing, you know, typically can produce a 0.9 sphericity. But the yield can be quite variable from, you know, as little as 30% to as high as 60% based on the process that you might be going into. There are certain materials, titanium, Ti-64 being one of them. There's only a need for powders in that 15 to 45, 20 to 63 range, which is about 40% of the yield, meaning that we're lumping all of the cost of production on, you know, less than 50% of what we make. And in there, that's a commercial inhibition to titanium, you know, taking off as a material of choice. Through our process, we can tailor the size and we get nearly 100% conversion efficiency. The sphericity, you know, we can match a little bit to the desired piece of the process. Our powder size distribution is nominally 30 microns, so we can take in a customer requirement. We look at a D50, and then we can shift that up or down based on the requirement. So you can kind of see what, you know, this is where we get the size efficiency. So the powder by the hour, this is, you know, an idea. This is a step change. This is a concept that you were looking at. And so this is the idea that we set our machine down at somebody's site. They feed it with bar stock. Bar stock for 70-75 material goes for about $13 a kilogram. You can produce atomized powder for less than $60 a kilogram through that process. Now, whether that goes into a DED machine or cold spray or other printers, whether it's feeding a spherodizer, you know, at some level we don't care. We can match, you know, to the input that's necessary. So theoretically now you can have the powder production going from bar stock in to part or spherical powder out effectively in a very linear and continuous process. We have signed a couple of cooperation agreements with Speed 3D and Formalloy around this concept. So, you know, with those machines, not exclusive, but with those machines, you could sit our powder generator next to it and feed it on a continuous basis. Our aluminum and copper powder, you know, here's what it looks like, is this prismoidal type shape. This is, you know, this can be further optimized. Here's another example where we took the copper material and ran it through a spherodizer in concert with 6K, and, you know, get nice controllable spherical particle out of it. If you desire spherical particles, that's a possibility. We've certainly shown that it produces good prints in conventional processing through binder jetting and through powder bed diffusion without it, but we're certainly conscious that for the last decade, we've been telling people that spherical particles are essential. And now some of the evidence is showing that maybe spherical-like particles are helpful. So we'll talk about that. Really, I think what we're looking at is that it's important to get to a certain bulk density in the powder bed. Beyond that, we're feeding a weld pool, and tap density is interesting. So these are some of the measured values that we have. It kind of goes back to the previous discussion about the rotating drum. The rotating drum is more suitable for a powder bed or binder jetting environment than the Hall flow is, because rarely do you have an instance where you're flowing powders through a circular orifice, specifically a very small circular orifice. So, it's a proxy for what we want, which is powder movement. If we look at, we've done some CT work with the University of Pittsburgh. So we've taken our powders and we've also spheroidized them. So, what you don't see here, because you can see straight through it, we don't have any defects. We convert effectively whatever the bar stock material is. We'll retain the microstructure. We can retain the heat treat or temper of the powder, of the bar stock into the powder, because we don't really introduce any heat into the product. There's no melting. We don't change the state of matter. So it's a very interesting process from that. We've done some comparisons with Purdue University here on different things. And so on our first chart, we looked at printing a 7000 series aluminum. So we started off with 7075. We added the HRL process to both materials. So gold is the metal powderworks powder. Gray is the gas atomized powder, and effectively, you get the same properties back out. I could say that metal powderworks is slightly higher, but we're talking single-digit megapascals. In any event, if you were to compare this to 7075 plate out of MMPDS on an A basis, so this is minimums to minimums, we are, exceeding the minimum for 7075. So this is very promising. If you look at the center picture, this is just a powder fingerprint that Purdue looks at. I think at the bottom line, you're looking at the blue lines and the gold lines, pretty much the same. And it's not identical, but it's basically processes the same in a lot of different metrics. And on the right, we show the rotating drum. And so we see some separation as we move to higher rotating speeds, which would be akin to a recoater blade. But with feedback that we've gotten from some people, we found that the faster we recoat, the better performance we got. The bottom line with this graph is that 20 degrees of difference really isn't meaningful in terms of powder behavior. It is academically different, but maybe not meaningful. So we have done some testing in a lot of different processes. So here's that solar car part in a powder bed fusion. We've done the aluminum material in 3 different styles of printers: EOS, 3D Systems, Renishaw. We did some work with Illinois Tech, so they have done binder jetting of our copper powder, and you can kind of see here what it looks like. We are doing copper printing with powder bed currently with University of Waterloo. I've got a couple slides here in a little bit. We've done some cold spray work of both copper and aluminum, kind of see the adhesion interface that we get. So we're working to dial in this. We're now giving the cold spray people more degrees of freedom. We can tailor the hardness of the powder through the heat treatment, and that controls the deformation behavior. We've also done some DED work with the form alloy process. So some preliminary work here showing that, in fact, the powder moves through the process fine. We've got some copper work done at RMIT University on a Trump system. We're getting ready to do some work with NASA on a RPMI system in concert with Elementum 3D. So what was really interesting, we did this, we've been doing this work with MSAM at University of Waterloo. And copper, as you know, is a highly reflective material. What we found was that we've been able to get to high density, 99.9 density, but at 40% less power, simply because more of the laser power is absorbed by the particle. It's not reflecting off because we're not making a shiny round sphere. So what this means is that you will see less evaporation inside the chamber. You will see less residual stress in the parts. And from a macroeconomic standpoint, it means that more of the conventional metal printers that are out there can process copper. So we're just using, a regular laser. It's not a green laser or blue laser or anything like that. We've basically designed a particle that helps the process using laser light. We've also done a life cycle assessment, and what we found was that our process emits almost 80 to 90% less CO2 than gas or water atomization. And we think that this is really interesting and very meaningful. We don't use a lot of energy in our process, and of course we don't emit hardly any CO2 emissions. And when we switch over to the use of renewable energy source, because primarily the only source of CO2 emissions that we do consume is electricity, we can improve that by as much as 97%. So we have a highly efficient, highly sustainable powder production method. As a company, we are moving into a production mode in a production facility. Our new production facility is here in Pittsburgh, Pennsylvania, at Neighborhood 91, which is the additive manufacturing production campus near the Pittsburgh airport. We are in with a host of other companies that are making parts using additive manufacturing. This is a production campus focus. So our next door neighbors here to the right, you can see we're just getting doors. We have windows. Hopefully we'll be taking possession of the building any day now. Our neighbors on the right are Wabtec Corporation. They've got an SLM 800 making parts. Our neighbors to the left would be Hammer Industries that have a Speed 3D cold spray machine doing advanced coatings. And further down in the building is Cumberland Additive, who in this particular facility have a SLM 500 and CNC machining capability. So as that campus grows, we expect to grow with it. If you kind of putting this all in context, so why are we, beyond that we've got a new process, which is, certainly interesting, why does it matter? I mean, why did we do it? So if you look and you're interested in powder fed systems, macroeconomics, metal powder market is a $14 billion market. It's not growing very much. The only growth is in additive manufacturing. Metal powder, while the metal market is about $2 billion, the metal additive powder market is around about 600 million, could be up to 800 million this year. That market is really the only thing that's growing within this metal powder market. So it's very interesting that that's the case. 95% of the metal powder market is water atomized. Currently, additive manufacturing uses 0% water atomized powder. So it means that we're only utilizing 5% of the installed capacity. At some point, this is going to restrict the growth of additive manufacturing if this were to continue. Most of the materials that are of interest to additive manufacturing are maybe different than what the metal powder market grew up with. So it's a lot of stainless steel. There's some Inconel 718 out there. There's some other materials, but we need to see more materials if additive manufacturing is going to really grow as everybody expects it. This is the problem, which is it's hard for it to grow when you get low yield out of the size fractions that's necessary for additive. So this is where perhaps we come in to fill part of this. What we're not telling you is that we're trying to replace atomization. If anything, we can be sympathetic to the atomization market. You can take the oversized powder, extrude it, hip it, sip it, turn it into bar stock, and then we can convert the rest of that to powder. So more like a closed cycle efficiency loop. Also, all additive processes don't want or need the same powder. So we talk about these different additive processes. Largely, we talk about additive, as if all processes are the same, which they aren't. It's a pretty diverse space at this point. I'll get to a bit more of that in a second. So, when we talk about spherical and non-spherical, I think we're starting to overcome the desire that super spherical is really desirable, because now we're seeing that denudation actually impacts the ability for us to retain some tolerances and surface finish. And so denudation simply is, think of it simply that if it took very little energy to get the powder into position, which we all like, it also means that it takes very little energy to get it right back out of position. In any additive process, you're putting a force on that powder. So as it's sitting in a bed and the laser is moving around it, the laser is exerting a force on the powder. This feeds the technical term of denudation, which is the powder moving. So it's no longer where you want it to be. It's partially the reason why we see spatter in some of these processes. In binder jetting, it's still an effect. We did some work with Carnegie Mellon years ago where we were able to visualize the impact of the binder. The binder droplet is coming down on that surface at 8 meters per second. And if you have a highly flowing powder, it's basically like a small bomb detonating every time the binder comes down. So you're displacing the powder as the binder impacts the surface. So what you really want is powder that has good movement, but not the most movement. And so what you want it to do is get into a bed and kind of situate, and so then it resists the energy from the laser, from the E-beam, from the binder, or whatever the source of energy might be. And so quite simply, if you think about natural packing factor as opposed to tap density, none of these systems have truly a tapped density situation. We're not tapping any of these things 100 or 1,000 times to get perfect density out of it. Natural packing factor is I throw powder down onto a table or into a jar and, naturally packs. Ellipsoids naturally pack very well. They pack as good as spheres do after several taps. So just ideas, again, for you to think about. And when we look at sphericity measurements, it starts to become very hard to tell why a 0.8 sphericity measurement is so much different than a 0.89 or a 0.9 sphericity measurement. So, things aren't always what they seem. Not all materials form nice spheres in an atomizing environment. If you look at aluminum atomizing, for example, tends not to form the nice spheres that Inconel or nickel or titanium do. So all of these things play a factor. If we look at the end use, so some work done by Barnes Global Advisors. So in really what you need to look at here is that we're growing from about 24% in additive manufacturing to about 44% estimated by 2029. So again, the growth is going to come from additive manufacturing, not so much from the other powder consuming technologies like MIM, powder metallurgy, etc. If we talk about why this matters, so as the printers get more productive, the part cost decreases, but the percent that powder represents grows. So unless we improve the productivity to manufacture powder, this situation would be true. So a couple of years ago, let's say the powder's $150 a kilogram and doesn't change over time. 2 years ago, the powder's roughly 8% of the cost. This goes to the specific part here. Most of the cost was tied up in the print and then the post processing. Today we're looking at because the printers are becoming more productive, we're seeing that the printing cost is decreasing and the post process as a function of the whole is increasing, and also the materials have increased because those other two things haven't changed, whereas the printer has improved. Now, if we fast forward to thicker layers and further compressing and improving the productivity of the printer, we see that cost continuously shrinking. So we could see the powder be as much as 35% of a printed part. now, more pressure is going to be exerted on people to figure out how we're going to improve that situation. This chart, also done by TBGA, means that we're predicting here in the short term, there's going to be a crossover between demand and supply. And if the capacity doesn't increase, typically we all know what happens with supply and demand when the supply is low and demand is high. So this is not going to help us in the future. And it kind of goes back to that original comment that if additive persists in only using atomization, it's really limiting its own growth, because it's going to take a lot of funding to start punching out more atomizers. Something else to think about. So we did a quick kind of simplistic exercise. So if you think about kind of bringing it back to the theme of our topic today, design for the AM process with an impact on materials. So we think about qualification of new materials. Again, qualification requires a repeatable and reproducible processes. Stability and consistency in the material feedstock is critical. Today, there are only 16 released AMS specifications for powder. So that means that there's less than 16 alloys for additive to use if they're going to be qualified through an AMS specification. However, there are over 2,000 released specifications for bar stock. So right there, we believe that Metal Powder Works can improve the number of materials that are available, because the ability for us to qualify powder should be very high. We start with a qualified certified bar stock that has a specification. We're not melting it. We're not changing the state of matter. It's a continuous process. So we can create a specification around that, and we can meet most of the AMS specifications, by and large. They don't specify that you have to melt the material to create powder, but we need more specifications for powder. That's the bottom line. So if we think about designing for the process, do all processes want the same shape, size, and condition? So simply thinking, if you look at any powder bed fusion process, we need to get the powder into position, i.e. the bed. The bed needs to be some minimum density, so that if we create a weld pool, we can feed it and get high density. And it needs to absorb energy efficiently. We need not to reflect the laser light away, because, again, thinking as a materials engineer, if you're dumping more and more energy into my material just to get it to absorb the heat and melt, then once it's liquid, you're going to drive off, ruin my metallurgy that we've taken great pains to give you. And then you're going to create additional residual stress considerations. On the cold spray side of thing, what you're really interested in is consistent deformation behavior by the powder. And so our ability to retain a temperature or heat treatment on the powder would be central to being able to certify a structural repair. Certifying a structural repair in an atomized powder that hasn't been heat treated, because that aluminum, for example, will just continuously age at room temperature. So your performance is then changing, week by week. On directed energy deposition, we talk about powder flow via forced gas. So it's a very different situation than everywhere else. Similar to, cold spray actually doesn't desire a spherical powder in the first place. For DED, the ability to control size, almost ties to surface finish pretty directly, but you need consistency for this material delivery. And then I call it center-based rather than specifically binder jetting. So, any of the technologies that derive their density from sintering, having multiple points of contact is desirable. Our process, because we mechanically drive the powder, we have high strain energy surfaces. Theoretically, those should give you a lower sintering temperature. So there's hope that having multiple points of contact creates multiple sintering initiation points. And that's what I have for you. So hopefully my chef analogy was appetizing and entertaining. if nothing else. So with that, I'm happy to take any questions that there might be.
Thank you, John. There's some questions in the chat, so I'll shout them out for you if you'd like. So size ranges, what size ranges are you able to process? So I think you showed laser powder bed, electron beam, etc. The question is, can you go down to sub 5 micron powder?
So I think sub 5, that certainly might be a challenge for us, mostly from a conveyance standpoint, but also from a tooling geometry, to be able to make a tool with that level of fidelity to it. So we're currently working on some 10 micron-ish powder for some people that want that. Interestingly, we're also getting requests for larger particles. So yes is the answer. The degree of difficulty changes obviously as you get closer and closer to maybe 1 micron. The process changes as you get higher than, say, 100, once you're hitting like a 200 micron type particle.
Okay, great. Next questions, there's a few here. So how cost efficient is this versus gas atomized? I think you kind of covered cost efficiency.
Yeah,
already. I think anything to add?
Yeah, I think mostly our efficiency drives better cost than gas atomized. Where that's not true, we'll tell you for a material like Inconel 718, where there are markets for all of the different sizes of powder, that's an efficient way of doing it. So our ability to compete with 718 and gas atomization, I don't know that we need to try to do that. But where we're very competitive are materials that do not have markets outside of the sort of notional powder bed cut. Will always be cheaper than atomizing.
In those cases, have you any plans to trial, hit scrap? So rather than look at Inco as an example, if it's quite a nice product in terms of atomization, but if there was an opportunity to hip scrap turn-ins or powder that can be fed in, have you looked at that as a way of reusing and adding additional sustainability focused value?
Yeah, we haven't demonstrated it, but we are currently we've got material in various states with different customers. So one is we're taking their oversized powder or used powder, and we're hipping that to a bar. Another customer, we've taken, they have a proprietary aluminum alloy, so we've taken all of their oversized powder and we have extruded that to a bar. And so the idea with the second one is that we will they'll blend in our powder with the atomized powder, but basically they're getting, let's maybe not say it's 100% efficient, but let's say they go from 50, 60, 70% efficient to 95% efficient overall. So yes, we are looking at that with various people. And the other interesting case that's popped out is because we use a round bar, we can take drops that are left over from other manufacturing processes and utilize that in some instances. So there are a couple different ways of looking to deploy the process depending upon the desirable outcome.
Right. Next question is, can it be used to laser powder bed machines? I think that must have came early. You've covered that. How do you control the particle size distribution?
Yeah, so the way we started the idea in the first place was that we said this process, whatever we do, has to be consistent, and we have to be able to control size. And so we start off with a spreadsheet and kind of went from there. So we control the size distribution through a combination of the material science, the process algorithm, and the tooling geometry. So all of those three things come together that allows us to make the same thing every time. So in that, you get a very narrow powder size distribution, and you get very consistent particles. So recently when we supplied MSAM with some additional powder, when they did the particle measurements, the D10 and D90 a year later only varied by 2 microns. So our product is very, very consistent.
Stuff. And the final one on the chat: could Thai bar be processed, and is any extra preparation needed to produce copper powders using copper bar? 2 questions.
Yeah, so the first one, I think the Thai, depending upon what alloy we're talking about, so we everybody and their brother asked us about titanium, but we're not really sure why. There's a lot of supply for titanium powder on the market today. There are some technical challenges for us. Titanium is a tough material, so it doesn't sort of necessarily machine well. Yeah, so for Thai 6-4, commercially, we're not very interested in that material, just because we look at the competitors out there and we're not super desirable and going head to head with them. So we see just that market being well and truly oversupplied. For other titanium materials, I think that could be very interesting. So we'd be interested in that. I think possibly gamma would be a really interesting material for us to look at. On the copper side, right now with the copper material that we're using, it's pretty much generate the copper and it goes right into the printer. So I don't know whether a lot of times there's some hand wringing over the morphology of the powder, but that 99.9% density figure is the powder as is.
How many of the 2,000 variety metal bars in ESM have you produced powders for?
Good question. As a startup, I think we're hitting less than 5. So we've got a long way to go.
I think it'll be worth that kind of line in the sand when you pass the 14 mark and you've then surpassed the typical atomization. I guess as a UK AM guy or gal, how do we engage, John? Is there an area that a material that you'd like to put on the table, or something you'd like to be looked at, whether it's UK or US? What's the next bit for us to try and bring this together, this industrial academic collaboration thing? Is there any low-hanging fruit for you?
Yeah, I mean, I think the best thing for us is the stuff that we do know how to make, which is kind of the 2000, 7000 series aluminums and copper. If people are interested in that, we can supply that today from our facility in Pittsburgh. We're also interested in developing what we call a developer network. So with a mindset that there are 2,000 approved bar stocks out there. If we try to do that ourselves, we'll be here forever. So if there's a network of let's call it material developers that have our machine, maybe at University of Bolton, that's also a way that we can engage and kind of hits that triangle with university, industry. Well, I don't know what the third leg of that triangle is, but
okay. And so the final question is: dealers located globally? I think it's right. So there's no dealers. This network is exactly the way you envisage this moving forward.
Yeah, we're a young company, so we're really just emerging out from total quiet. We will supply. Initially for 2023, we would need to supply anybody from the Pittsburgh location, but we're certainly open to conversations on that.
Excellent. Thank you very much. While we'll wait for any other questions, thanks John, and also Dwan and Jimmy for your time today.